Thank you, everybody. Thank you for coming tonight. I'd like to start with a question. And it's a ridiculous question. At first glance, it's a ridiculous question. My question is, did the flood basalts, did the giant lava flows in eastern Washington cross the Cascade Mountains here in the state of Washington? And at first glance, you're like, that is the dumbest question I've ever heard. Aren't we talking about the Cascade Mountains? Yes. Aren't we talking about this major north-south trending ridge? Yes. But it's more than a ridge. It's an honest-to-God mountain range with Mount Rainier volcano, with Mount St. Helens, with Mount Hood, with Mount Shasta, all the way down to Northern California. And there are mountain passes. Snoqualmie Pass, many of you drove coming from Seattle to drop over here to Ellensburg. It's a big mountain pass with elevations, 3,000 feet elevation at Snoqualmie. 5,000 feet elevation at higher mountain passes. We could talk about White Pass, Stevens Pass. We can go up to North Cascades Highway. We can go to Chinook Pass. These are the major mountain passes in Washington. It's a mountain range, man. And some of those high ridges go up to 10,000 feet elevation. And the summit of Mount Rainier and other cones are over 12,000, 14,000 feet above sea level. So what do I mean? Did these giant lava flows cross the Cascades? Are they like flowing uphill or something? I don't get it. Like you're missing the hook. Well, let me try to draw the concept and we'll see if you still think it's ridiculous. You probably will with this first sketch, but maybe by the end of tonight, you'll start to think, well, maybe that is a decent question. Because there's a couple things that I didn't quite realize before you started this thing. So let's just draw, let's not screw around. Let's just draw a big cross section. And here's Seattle, Washington. And here's Ellensburg, Washington. You're sitting in Ellensburg. East off this way, west off this way. And here's the profile of the Cascades. You want Ellensburg here? I'll do it. Ellensburg and Seattle. There were enormous lava flows. I'm continuing over here now, okay? There were enormous lava flows that came out of fissures, cracks in the earth, over here by damn near Idaho. And those cracks opened up. I'm improvising already. I wasn't planning on using a twin board setup. This is kind of fun. And enormous lava flows came out of those cracks and started flowing west. And the conventional message is they reach the Cascades and they run into a roadblock. They run into the Cascades. They start flowing west and they run into this roadblock and they stop. This is the conventional story. And maybe there's another eruption. And maybe there's another eruption. And maybe there's another eruption. Maybe there's 300 separate eruptions, which is true. And maybe many of these lava flows have an average of 50 feet or even 100 feet thick, which is true. They are giant, orange, Hawaiian-like lavas erupting in eastern Washington. But again, what am I asking tonight? Am I asking that, what are we talking about? We're going to just keep doing this until the lava flows go over the crest of the Cascades and get to the ocean? Forget about Seattle, get to the Pacific Ocean? Are we really seriously asking that? Well, it's not my question. It's a question that was posed in the 1940s, in the 1950s, the 1960s, and the 1970s. Mainly geologists at the University of Washington in Seattle, by Cascade geologists who've thought a lot about the Cascades and have done a lot of time working in the field in the state of Washington. J. Hoover Mackin, Bates McKee, Eric Cheney, a Portland State University professor, Paul Hammond. Many others had this concept of these giant lava flows crossing the Cascades. And you're like, I don't get why they're thinking that. I know these are giant lava flows, but they can't be that big. They can't be that thick. If you know the history of the Cascade Range, you realize a very important point. The Cascades have been around for 46 million years. But the Cascades have only been high Cascades until recently, less than 10 million years ago. And these eruptions happened 16 million years ago when the Cascades were low. So right off the bat, our cartoonish picture is not quite as outlandish as previously thought, because the history of the high Cascades and the uplift to make high Cascades is younger than the lava flows themselves. And in Geology 101, uplift intensifies erosion. Now are you willing to listen? Okay, so let's expand on that, but that was the attempt to hook you into this story. Let's do some Geology 101 just to get everybody involved. We have some kids here. We got some folks from all over the place, far-traveled folks here. California, East Coast, Canada, etc. Wonderful to have you all here. So to get everybody on the same page, I think most of us know that the Cascade Volcanic Arc is the result of two tectonic plates colliding. It's a convergent oceanic versus continental plate boundary. It's an oceanic subduction story. We're generating magmas in the mantle wedge. We're rising those arc magmas to the surface, and we have continuous volcanic eruption. How long's that been going on? 46 million years. 46 million years of volcanic arc. Did anybody catch the age of the flood basalt eruptions? I gave you one number very quickly. Did anybody catch it? 16, correct, 16. And we'll look more carefully at that number 16 in just a second. But, okay, so the history of the Cascade Arc is much older than the relatively short-lived flood basalt story. Okay, let's clean up my sketch and add a couple other concepts. And just this afternoon, as I was putting the rest of this lecture together, I ran into a question that I hadn't thought about before. I still don't know what I think about it, but we'll share it with you. This is a lecture that's different than the last couple of nights. This has an open end to it. This is almost an unsolved mystery. This is almost possibly a call to action for some young, bright geologists who want to pick up the pace and work back on this story, because really nobody's been talking about this question about the flood basalts crossing the Cascades in the last 50 years. It just kind of died, kind of lost its mojo. But it's always in the back of my mind. I've been teaching here for 35 years. I hear it occasionally, and I'm like, yeah, that is kind of an interesting question. I wonder if anybody's worked recently on it. Maybe we will have some of that. Okay, let's get to this thing that I had a new thought about just recently. I think many of you know, maybe all of you know, that Cascade Range has a major hole in it. There is a place where you can drive right through the Cascades, or you can take a boat or a train or a stagecoach or whatever, Lewis and Clark, go right through the guts of the Cascade Range. And that's following the Columbia River. The Columbia River comes out of British Columbia. The Columbia River works its way to the Pacific Ocean. This is the Columbia River Gorge, the state line between Washington and Oregon. My new thought 3 hours ago is that I've always taught that the Columbia River is older than the Cascades because it cuts through. And my thought was, I think it's a conventional thought, is that if you have this major river going through a major mountain range, the river must have been there first, and then the Cascade Range has lifted on both sides. But I just assumed that for the last 46 million years, there was substantial mountain range there. And the new information that I've learned this winter has been that there were times when this Cascade Range was very low, and there was one brief time in geologic history where the Cascades were just not there at all. So I wonder if this is really true, that the Columbia River is far older than the Cascades, but I don't think that hurts us too much tonight. What I want to emphasize is that if you go and follow the Snake River through Hell's Canyon, you follow some other tributaries of the Columbia, you've got major drainage of the inland Pacific Northwest coming through the Cascades and coming to the ocean. And why is that important? It's important because it is true that you can follow these giant lava flows through the Columbia River Gorge. I think you all know that as well. That if you go to the walls of the Columbia River Gorge, here's our lavas erupting 16 million years ago. They are funneling through the Columbia River Gorge, and our lavas are fanning out again, is the conventional story. And so we can go to Aberdeen, Washington, we can find some Columbia River basalt lava, the flood basalts, in other words. Those are interchangeable tonight. Columbia River basalt group and flood basalt, same thing. We can go down to Newport, Oregon, and find those flood basalts. We can see the flood basalts at Portland, at Hood River. We can find the flood basalts all through the channeled scablands. We can find the basalts up to Spokane. It's a regional story. And even though these lava flows are enormous, they are watery. And so they are not flowing uphill. They're spreading over the landscape just like water would spread over the landscape. They are called flood basalts. And so there was a natural pathway 16 million years ago to get these things to the ocean. But that's not our topic tonight. The title of the talk is not, did the flood basalts go through the Cascades? I think we all know they went through the Cascades. I'm asking, did they go over the top? And the key understanding is that the high Cascades are a recent thing. Most of the history of Washington is relatively flat. Most of the history of the Cascades is relatively low elevation. And this high Cascade story is younger than 10 million years old. Data coming for that in just a second. Oh man, the energy is outstanding. I mean, I know this is the third night and everything, but God, I'm just riding high off of this electric silence. Thank you. Thank you. Seriously, thank you. Okay, yeah. Applause for yourself. Why not? Why not? Okay, let's add a couple details now and transition to the next part. I got 3 acts, and that was essentially the first act. I think we know this stuff now. Let's get rid of it. That was the cartoonish portion of tonight. Now, if we're talking about these eruptions, and we are, some of you have a Yellowstone hotspot kink. I understand that. So let's work with that. So these fissures, it turns out, are with an orientation, a northwest-southeast orientation, that is really paramount throughout the Pacific Northwest. That grain, that lay of the land, that northwest-southeast trend is not an accident. And it was a surprise to me about 10 years ago to realize that when these flood basalts came out of these cracks, the cracks were already there. It's not like the cracks formed in response to some sort of Yellowstone hotspot. The Yellowstone hotspot found itself under this part of the crust that already had this structural grain, and that mantle, that heat source, just took advantage of those northwest-southeast trending cracks. So my point is, yes, we're going to get our eruptions of the flood basalts. We have plenty of professional maps to look at momentarily. But 16 million years ago, we had a broad regional head of this Yellowstone hotspot, this Yellowstone mantle plume. And once that Yellowstone mantle plume crossed into Idaho, the signature of that mantle plume became much more narrow. And there's still debate about why that is, but the general story is you're transitioning from Yellowstone mantle plume, trying to get up through a Farallon plate that's subducting over the top of it. Plus, you're dealing with exotic terrain bedrock, which is kind of a cobbled together mess, a quilt or a fruitcake. And once you cross the western Idaho shear zone and get into old-fashioned North America, that's the craton of North America. That's a far older, a far more stubborn, substantial, thick piece of basement of old North America. It's harder to get magmas up through that craton. And so I think most of you realize that by the time we do that, and go from 16 to 10 to 5 to 0, and have an age progression with the Yellowstone hotspot marching its way towards present-day Yellowstone National Park, it's North America moving that way over a stationary mantle plume. It's not the opposite. But that signature and that Yellowstone hotspot story does enter in briefly tonight. It's not a major topic of ours, but it is an underlying story with these lavas. What I do want to focus on is to expand on what we know about the stratigraphy of these flood basalts. And we have some new dates They're a little bit different. If you're a fan of geology, they're a little different than the normal routine. So what I want to emphasize is that there are 5 subgroups within this stack of Columbia River lavas. So if we think of a German chocolate cake with 300 layers of chocolate layers within the cake, that's what we're talking about here. 300 separate eruptions out of these fissures with a Yellowstone mantle plume with a regional head feeding that story. It's this middle section of the cake that is 75% of the cake, and it is robust. I'm going to draw that differently. I'm not happy with that. I want to really emphasize that the middle part of the cake, which is 3/4 of the volume of the cake, is really the portion of this flood basalt story that we are demonstrating tonight. And I want to emphasize a couple other things as well. So down here is the beginning of these basaltic eruptions coming out of the fissures. Up here is the end. It's not happening today. When you drive to Palouse country for a football game, you don't fight lava flows on the way. It's totally over with. But between 16.5 million years ago and 16.1 million years ago is the Grand Ronde time. The Grand Ronde time. And as I mentioned, 75% of the total volume of the cake is Grand Ronde lavas. And these lava flows are monstrous in individual thickness. They're the ones that potentially made it all the way to the coast and potentially crossed the Cascades, as we're talking about tonight. And there's so much time and so much action during this Grand Ronde time that we actually have 4 different chapters known locally as R1, N1, R2, N2. So there were magnetic flips of the planet, normal polarity and reverse polarity. Switch, 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 switch during this Grand Ronde time. So globally, the Earth's magnetic field had a dominant magnetic north pole, then a magnetic south pole, then a magnetic north pole, then a magnetic south pole through this time here. That's really one of the main ways to keep track of which of these Grand Ronde lavas we're talking about. I'm setting you up now to realize that it's really this N2. It's the youngest of the 4 Grand Ronde chapters that are the potential crossers. And we're going to be hunting. It's like a treasure hunt. We're going to be hunting for some N2 Grand Ronde lavas and see if we can find any of them today up in the high Cascades. I wouldn't waste your time if there weren't a couple of kernels for us to find that are often overlooked. But it's not the whole stack. And a concept that Andrew Sadowski from the Washington Geological Survey has gotten into my head recently is that many of these earlier Grand Ronde lavas were flooding the low spots in eastern Washington. And they paved the way for a potential crossing of the low Cascades. So it's not like the first lavas are going all the way to the coast. We have all the low spots filled in earlier Grand Ronde time before we get to the main story here. It's the N2, it's the Grand Ronde lavas, just a little bit older than 16.1 million years ago, that are our main friends that are potentially crossing the Cascades. Very good. Now, I teased the idea that if you look at the history of the Cascade Range, you've got 46 million years to work with, but this past winter, we took our time trying to go from old to young throughout the history of that Cascade volcanic arc. And much to my surprise, and I think most of you, if you were part of our learning community, is that if we go from 46 up to 0, the history of the Cascade volcanic arc, the history of this thing here, the early days of the Cascades, in the 40s, I had shorthand known as decades. So in the first few million years of the earliest days of the Cascade volcanic arc, the indications we have is that the Cascades were low. And you're like, what exactly does that mean? How big were the mountains? Come on, that's 42 million years ago. What do you expect? But there's no indication of a high topographic divide in the early days of the Cascade volcanic arc. The shocker is that during the 30s, roughly between 36 and 28 million years ago, Green rocks up in the Cascades today, collectively known as the Ohanapikosh Formation, have all sorts of details, I'll show you some field photos in a bit, that say that those eruptions in the Cascades were happening underwater. The Ohanapikosh Formation between 36 and 28 million years ago, this says 30s. We have no Cascades, not even low Cascades. We have nothing. It was a flat plain, and there was even Pacific Ocean water, I guess, encroaching into here. And the details that are now high in the Cascades with the Ohanapikosh tells us about these cinder cones and other kinds of all sorts of interactions between magma and water, but the water was ocean water, Pacific Ocean water. So that was a shocker to me, and I thought, okay, well, at least we have the low Cascades in the 30s, but certainly we're going to get to some high mountains as we get younger. Well, also a surprise to me, and maybe many of you, once we get into the roaring 20s, between 26 and about 18 million years ago, we still have some cones, we have some stratovolcanoes growing in the Cascades, but it's a coastal plain. There's all sorts of sedimentary rocks during the 20s that tell us we're still at relatively low levels. Even into the teens, between 20 and 10 million years ago, most everybody in geology, when you start looking at the details in the Cascades, say that those are low hills. They're not the high Cascade. Do you remember the age of our lavas? They're right there on the board. Come on, man. 16 million years ago is when we're doing our flood basalts from eastern Washington potentially to the coast. And we haven't even started a dramatic uplift of the Cascades. Now, in February, I was trying to interview whoever I could, geology-wise, to get some specific answers on when they thought we went from a low set of hills in the Cascades to a towering mountain range that we have today. Basically, when are we going to start this rain shadow effect that we have today? You know, it's a desert over here. Beautiful weather this weekend. I hope you got out and enjoy our beautiful desert air here east of the mountains. But when did that rain shadow effect begin? Depends who you talk to. Everybody says the rain shadow effect starts younger than 10 million years ago, meaning the high Cascades from tectonic uplift are starting younger than 10 million years ago. Sky Cooley in the audience likes the number 7 for reasons that we'll look at with the slides. Other U.S. geologists think maybe the major uplift started 3 million years ago. By God, now we are in the Ice Age and we're starting to jack these mountains up to their high position? Our ridiculous question at the beginning becomes less and less ridiculous when we realize how low, how non-existent, how unassuming the Cascade Range was during most of its history. Awkward pause. Okay. So let's look at Washington and think about what our choices are. If we're willing to entertain this crossing of the Cascades, do we have a couple of options? There's a greedy option and maybe a more reasonable option. Okay, let's put some detail on. Here's Spokane. Here's Seattle. Here's Ellensburg, where you are sitting right now. And let's have this map be 16 million years ago. Let's have it happen during our flood basalt time. That's not good enough now. Let's have it during our N2 time within the Grand Ronde. Okay? Our fissures are over here. And it's not just a Washington story. I'm Washington-centric, but you know that Oregon is a major part of this story as well. And we're going to have our lavas coming out of these cracks and flowing west. The greedy option is that even though during that time we have low Cascades, And let's put some cones in. Let's put some stratovolcanoes, some beautiful snow cones that are the size and shape of Mount Rainier today. Let's make them up. They're not Mount Rainier. The cones we have are less than 1 million years old. So I'm going to put some stratovolcanoes in that are made up, but probably existed in some form in the Cascade Volcanic Arc. Let's give us 6. We only have 5 today in our state. Let's give us an extra one, okay? So these are stratovolcanoes. I think the 2 options that are possible, the greedy option is that we're truly going to bury everything. We're going to bury the low hills between the cones, and why not? If we're greedy, let's do a good job about this. Let's have everything cross. Do you want to need a cross-section of it? I kind of did it before, but let's do it again. Let's have enough lava that we're actually, I'm laughing as I draw it, 14,000 foot high cone. Let's just go over at the top of the whole thing. I don't think that's crazy, and Don Swanson and others, Paul Hammond, who have mapped west of Yakima, had some evidence for these lavas totally burying tall cones, but we don't need to be greedy. I think a more realistic approach, a less greedy approach, is to have our eruptions, is to have our individual cones kind of be like islands in a low, broad region, topographically. And what if we just have some orange worms? What if we answer yes to the title of the lecture, did the flood basalts cross the Cascades, now that we know that they're low 16 million years ago? But what if we just find some low spots and some valleys that are successfully crossing through these low cascades? That's why I think maybe the Columbia River was not older than 46 million years ago. Maybe there was just a temporary low that the Columbia took advantage of 26 million years ago, 16 million years ago. But these orange worms are still going to allow us to get the lava to Western Washington. And over here at Gray's Harbor, Hoquiam, Aberdeen, there is some N2. There is some youngest of the Grand Ronde lava. And if you talk to almost every geologist today, they'll go, well, of course there's Grand Ronde lava at Aberdeen, you idiot. Haven't you looked at a map? You can just take these lavas, the Grand Ronde lavas, bring them through the former Columbia River Gorge, and then have those lavas spread out once we get to Western Washington and Western Oregon. And that very well could be the case. But you know what I'm asking tonight, and it's not just me, it's a few other geologists who have done a lot of work in the high Cascades. Why can't we have a shortcut? Why couldn't we have an overland route and an orange river of lava erupting out of some of the fissures over by Spokane and have them come through these low cascades, through some valleys that are there because of the structural framework in the Pacific Northwest as we still have today? That's the idea. So in many cases, we're setting up a lot of the images we have on the screen. I've got one more thing I want to do here on the chalkboard. Thanks again for the energy. I'm not totally making this up. I've already indicated that I am trying to resuscitate a set of questions that were in vogue 50, 60, 70 years ago. But that's north. And north of Ellensburg is a ridge called Mission Ridge. What's it made out of? N2, Grand Ronde lava. And it's thick. There's 1,000 feet of Grand Ronde lava just north of our town. That's west, northwest. That's Lookout Mountain above Cle Elum. That's the end of the line, quote unquote, for the Columbia River basalt lavas. That's southwest. I'm pointing now in real time to, some of you are looking. Yeah, I appreciate your enthusiasm. Yeah, just past that exit sign. That's Divide Ridge between Yakima and White Pass and the Goat Rocks country. There is some Grand Ronde lava in that neighborhood, even Bethel Ridge. And again, the thicknesses sometimes are more than 1,500 feet thick. So the last cartoon I want to draw for you is a cross-section from east to west. We'll put some jagged Cascades in here. Again, we can put Seattle and Ellensburg, but we could also put Yakima and Chehalis, or we could even put Chelan and Everett, I guess, depending on where you want to be in Washington, east versus west. And all I want to cartoonishly present to you is that here is our Grand Ronde lava that today is like a drawbridge that has opened up. I mean, I'm not making this up. This is real. So these are layers that we presume were originally flat-lying 16 million years ago. They're watery, they're thick, they're flood basalts. And if you want to, I wasn't planning on it, but let's try it. If you want to, let's bring them all the way through the Cascades. Where? Where can I bring them right through the Cascades? The Columbia River Gorge, thank you. So they were flowing right through the Columbia River Gorge because there was an opening. But we're thinking that maybe if we're in one of these orange worms in the low Cascades, maybe we had also some very flat, continuous N2 Grand Ronde lavas 16 million years ago. Are you with me? Since that time, we've had some warping, some arching, some opening of the drawbridge of the German chocolate cake. In the Columbia River Gorge, oh, this is going to work. My God, this is going to work. In the Columbia River Gorge, we still have those layers, and it's not a drawbridge. We can follow those layers. I'll show you some photos and some cartoons. In the Columbia River Gorge, those layers are continuous, but they're no longer flat. I don't know why I did a signature swale there. I don't think it's like that. But the point is, some of these Grand Ronde lavas exposed in the north wall of the Columbia River Gorge are 3,000 feet higher than their counterparts over here in eastern Washington. So this distance, this elevation change between the top of this N2, and here's the top of the N2 in the heart of the gorge, right above Cascade Locks. It's 3,000 feet higher at Cascade Locks than it is out there by the Dalles. The lava is not going uphill. Instead, the lava has been uplifted in the Columbia River Gorge younger than 10 million years ago. The question is, do we have something similar like that in Washington, north of the Columbia River Gorge? And you're like, I don't think so. I think the Columbia River Gorge is a very special place. I mean, it's not anything close. And I would nod and agree with you and give you nice penetrating eyes, and we all agree and we're connecting. But privately, I'd be thinking, north of Snoqualmie Pass, there's been way more uplift in the North Cascades than the South Cascades. I mean, there's bedrock dominating between Glacier Peak and Mount Baker volcano. Bedrock that is not even close to the surface south of I-90 in Washington. So as we go further and further north in the Cascades of Washington, I think we would have less and less success finding any remnants of these once continuous N2 lava flows. I hope you're following me. And so if we're greedy, we're back to the greedy before we go to the slides. I would want this if I really wanted to look for this story. I'd want two sides of the drawbridge, like visiting my grandmother in Duluth, Minnesota, and I would always be worried about the drawbridge. And is it ever going to come back down so we can drive back over to Grandma's house? It eventually went back down to allow a ship underneath. But that matching set is not there. It's the Puget Lowland. And maybe those broken parts of the N2 are somehow in the subsurface beneath all the glacial till, or some younger sedimentary material. But I don't have to put question marks here, because the elevations of Mission Ridge, the elevation, now I'm pointing to Lion Rock, north of Ellensburg. Elevation of Lion Rock is 7,000 feet above sea level. A portion of this N2 Grand Ronde lava is twice as high as the elevation of Snoqualmie Pass going over the mountains. So it is cartoonish on the east flank of the Cascades. And that's the ultimate reason that this idea of the flood basalts crossing the Cascades ever came to be. Okay, fast-paced. Some of this is old hat to some of you, but some of you, I think the flood basalt story might be brand new. Yes, we have an incredible amount of Pacific Northwest crust that was flooded by these 16-million-year-old flood basalts, including the N2 of the Grand Ronde lava. Cartoonishly, look at what they're doing. They're channeling those things through the Columbia River Gorge, which may very well be the story instead of our more radical crossing the Cascades story. But if we look carefully now, these are isopachs. So the total thickness of the German chocolate cake is 3 miles thick. We know that from drilling for oil and natural gas just north of the Tri-Cities of Washington. And then here's Ellensburg. We're getting to less than a half a mile thickness by the end. But what I'm asking tonight is that, has this always been a place naked of basalt? Or was there a continuous brown cover between this side and this side until recently, until we uplifted and erased much of the brown cover? That's ultimately what I'm asking tonight, if it didn't make sense to you before. So when those lavas were red hot and orange, here we are in Ellensburg on the edge of this whole thing. There's even some of these flood basalts creeping into Nevada. This is a regional story. I could have hustled and found some more modern footage from Iceland, but I didn't, so this is from 2014. This is the volume, this is the silica content, this is the viscosity we're talking about, but this is not the volume we're talking about. Our Grand Ronde lavas would have had a continuous orange cover over this entire field of view, not these piddly little rivers. And here are the individual fissures that have been mapped to feed a composite of all of the flood basalts. Again, we're thinking about the relationship between the Cascades, low versus high, and these flood basalts. Keep it going, boy. Now, here's the Columbia River itself, and you might be aware that the volume of the Grand Ronde lavas was significant enough to push the Columbia River up against its margin. So maybe this relationship is a vote against. Maybe it's a vote against our thesis tonight. Because why would the Columbia River stay right here? Why wouldn't the Columbia River have been pushed way the hell into over here someplace if the Cascades were so low at that time? I don't know. We're getting more and more into some open, debatable topics as we go through the rest of the slides tonight. The fissures themselves are still visible. There's spatter that you can see right at the surface from 15 million years ago. This is the Rosa lava flow, and you can see in eastern Washington a very special spot, the Eskier Ranch state land, that shows that beautiful spatter coming out of the ground. And then these dikes, these individual cracks that are now filled with lava, if you know where to look, you can find them. And they are majestic and were formerly underground, of course, but erosion has allowed us to see some of these incredible walls of basalt over at the cracks that were fed by the Yellowstone mantle plume roughly 16 million years ago. And then as you work your way towards the Cascades, this time in Moses Coulee, we can see 3 separate lava flows in this wall. They are enormous, continuous layers of German chocolate cake. This is closer to the source, the Grand Ronde River Canyon, in extreme southeastern Washington. Beautiful road. And if you look, you can see now a map of Washington. Here's yellow is urban areas: Seattle, Portland, Tri-Cities, Spokane, Ellensburg's this little yellow dot right here, and Yakima is here. And I want you to notice how flat everything is out here. That's not because of the Missoula floods. It's flat because our flood basalts buried everything, buried a rugged landscape. And in cross-section, Cindy Shaw from Tri-Cities shows our basalts slowly pinching out to nothing, and even to Lookout Mountain above Cle Elum, just one little chocolate dollop here as we pinched everything out. We're wondering if that is the true story, or if there was a continuous ramp of this German chocolate cake that went up and over before the radical uplift. I think you have it by now. The new dates that I mentioned are new precise dates from Jennifer Kasbaum, who was a graduate student back in the day at Princeton, back in New Jersey. So we had Ivy League geologists Mike Eddy and Jennifer Kasbaum and her advisor Blair Shane out here working with sedimentary interbeds between the German chocolate cake layers, including the vantage sediment, which is a sandstone, and there's also some pumiceous material within that vantage sediment. This is part of something known as the Ellensburg Formation, which I will be trying to learn new things about this spring with the class that I'm teaching. One of the first geologists to really study the detail of this Columbia River basalt stratigraphy and the sedimentary interbeds is J. Hoover Mackin. And he is, in my mind, the father of this idea about these giant lavas crossing the Cascades. Back in the late 1940s, he's the one that was writing about this concept. I'm not sure it was in the literature before Mackin, but this little pamphlet we're going to read a little bit from in a bit. And if you're jonesing for what we were doing last winter, there is a connection between our friend J. Harlan Bretz and Aaron Waters. Aaron Waters was also working with the stratigraphy of the Columbia River basalts back in the 50s and the 60s and the 70s. So buried in the literature are all these maps. I just made some orange colorful versions of the same thing for us, and we'll look at more of those custom-made maps in just a bit. But now we can see our magnetic reversals within this whole German chocolate cake story. These flood basalts are happening, and the iron particles, the paleomagnetic signature in these alternating basalt layers help us keep track of time. There's Blair Shane, who's from Seattle originally. He's now a young and a dynamic professor of geology at Princeton University, and he's had many students working in the Pacific Northwest now, including Jennifer, who published a couple of papers recently, and she was a former colleague of Mike Eddy, who is known to many of us in this room. Mike went to Princeton as well. So the idea is that we have new dates. These are brand new dates. So if you know the traditional dates for the Columbia River basalt lavas, these, in my opinion, are more precise and more updated because we're working with zircons and other uranium-lead series from sedimentary layers between the basaltic lavas. It's the Grand Ronde that we're talking about. There's the Grand Ronde and the N2, which is the star of the show tonight. But look at these other layers of lava that also came from the fissures that probably did not cross the Cascades because the volume was starting to wimp out. The Wanapum flows and the Saddle Mountain flows are piddly little flows compared to the Grand Ronde time. So let's not get carried away. I'm not talking about these guys or even these guys down at the low country being the main Cascade crossers. It's the basaltic andesites of the Grand Ronde that we're featuring tonight. So here's some maps to show how the Grand Ronde fit into this whole series of eruptions. In the earliest days of this system, the Amnaha lavas are coming out of the fissures down mostly in Oregon. But here we go. Here's the main phase of the flood basalts. And you're like, okay, there we go, case closed. You don't have orange crossing the Cascades. You're making this whole thing up. Are you paying attention? We're saying that, yes, today we don't have orange in the Cascades. But back then, we perhaps at least had orange worms connecting the dots between these two places. Let me give you another case study, not Grand Ronde time, but it's an interesting case study in my opinion. There's a pretty local fissure that fed the ginkgo flow, and the ginkgo flow has been mapped. It has a very specific mineralogy. It can be followed through the old Columbia River Gorge. And look at this here. There's ginkgo flow that you can find at Newport, Oregon. And yet today, let's look a little bit more at the ginkgo flow. So here's the ginkgo flow here. This is at Vantage, Washington. You're looking north. There's I-90 crossing the Columbia. Do you have your bearings? Ginkgo Petrified Forest State Park is over here. And this is 26, State Route 26. So at the base of the ginkgo flow are these amazing logs of petrified wood. George Beck's grandson is in the room tonight, George Michael. And there are some beautiful logs of petrified wood that are still standing, even though they were originally in this position in the base of the ginkgo flow that's been eroded away. But the point is, the ginkgo flow, not a Grand Ronde flow, but look at the ginkgo flow. It's conventional. Everyone agrees that the ginkgo flow had an arm that crossed not the Cascades, but the Coast Range between the Willamette Valley and the Oregon coast. But it doesn't look like that today. Instead, if you look at these Columbia River sands, which are at the base of the ginkgo flow, pretty dramatic boundary. The ginkgo flow is following this Columbia River through the Columbia River Gorge. I'm finally to the slide, I think. Yeah, here. Today, there is no continuation between the ginkgo flow and the Willamette, which is over by, what's the name of that park? We filmed there. Silver Falls State Park, I think. There's ginkgo flow there. And then there's ginkgo flow again over at Yakima Head. And there's beautiful orange plagioclase feldspars, gorgeous phenocrysts that prove that it's the ginkgo flow. But I'm trying to show you here in my homespun little way to label this, there is no connection between the ginkgo here and the ginkgo here. It's been eroded away with the uplift of the Coast Range. This is essentially a microcosm of what we're thinking about today. Does that work for you? And yet this is accepted by everybody, and yet the bigger story up here in Washington doesn't seem to have any traction anymore. I'm not quite sure why, if this one works for people. But we put this back in and everybody feels good about themselves. Because it's hard to imagine how the ginkgo flow what's the alternative? You would follow the ginkgo flow all the way to Astoria, and then what? This is definitely ginkgo at Newport, so you're going to have this thing flow like down the coast? And I don't think there is ginkgo flow. You can correct me, but I don't think there is ginkgo flow exposed in these portions of the Oregon coast, at Cannon Beach or whatever. But it's here at Newport. So that's kind of the concept we're talking about on a larger scale here. If I just finish out these beautiful maps, we can see the Rosa Flow, the Priest Rapids. We're now after the fact. These are the smaller flows. We're up here. We're up here. I just feel like I want to be complete about it. And there's a bunch of time transpiring between these minor flows, and so there's more and more of this yellow, which is the Ellensburg Formation. I'm setting you up for a key email coming in just a bit. Umatilla, disappointing. Very disappointing. I mean, these orange worms here are following river valleys. Isn't that what we're kind of thinking about crossing the Cascades? Why wouldn't, if you had more volume here, I'll stop. Okay, so yes, many of these orange worms are following former river channels, and those river channels are swinging through the old Columbia River Valley, 16, 15, 14, 13 million years ago. Kind of fun to see these individual flows mapped out, but again, the volume is very small compared to the volume of the Grand Ronde flows. All right, get off of this. Elephant Mountain, my favorite lava flow. Why? Because the columns are absolutely perfect over at Drumheller channels. This spot is also amazing right by Snake River, Calotis. You have 3 separate Saddle Mountain flows, each of these following possibly the same river channel, but the river channel keeps shifting around. Not really our topic tonight, but couldn't help it. I was probably just stalling, like, do I have enough for tonight? Let me throw in a bunch of these other slides. We got plenty. Come on, man, it's almost 8 o'clock. Let's keep it going. So back to the main point, I think we're there. Because when we're trying to uplift the Cascades, now I can't get a satisfying answer. And I think we're caught now. I think we're up to date with specializations of geologists working today. And I can't seem to get a straight answer. I'm a teacher, I don't do research, but I'm looking for people who've done some careful work. And I want to say, how much of the uplift of the Cascades is tied to the formation of the Yakima fold and thrust belt versus the north-south Cascade trend? Are those two separate uplift mechanisms? Are they somehow working together? So we're including the Yakima fold and thrust belt simply because we're taking these originally flat layers, which are now all cooled and dead and cold. Cooled and cold means the same thing. And we're going to start compressing them and rumpling them up. This animation cost us nothing and has paid for itself many, many times. This is the Yakima River Canyon between Ellensburg and Yakima. And it's this river course getting set and then these ridges growing. I'm asking now, is this just an uplift story in central Washington and going down to Oregon, in eastern Washington and eastern Oregon? Or is this uplifting, this knuckling up of individual ridges, is that happening throughout the Cascades as well? Did we have cross Cascade valleys controlled by this before we did some sort of renewed uplift in the heart of the Cascades from a different tectonic mechanism? And you're like, I don't know, I came for answers. Why don't you tell me something, man? No, we're done with that now. We're asking questions together and hoping we can motivate some new work. I hope you can feel that. So yeah, these gorgeous images. Here's where you're sitting in Ellensburg. Here's Yakima. And you can see that I don't know, can you squint and follow some of these ridges through the Cascades? There is some evidence geophysically that we can do that. And so all these deep canyons in eastern Washington might be a regional story that works in conjunction with the Cascades and not a separate animal completely. I just don't know of anybody making some definitive work tying these stories together. We're still just talking about the Yakima folds, not necessarily the Cascades, but sure, the clockwise rotation that we have dominating the Pacific Northwest, confirmed by geodetic arrays run by Central Washington University's Geology Department. That is a thing. It's driven by ocean plates offshore, but I really don't know if this is part of our young uplift story or not. We have canyons everywhere where the rivers are holding their own stubbornly against these uplifting ridges, back in that feeder dike country as well, in the Grand Ronde River Canyon. If we go into the big boy itself, the Columbia River Gorge, where the Columbia River has held its own against an uplifting Cascades, many of you know, strikingly, especially as you drive west to east, if you drive from Portland to here, I think everybody notices these incredibly tilted layers by Mosier. Those are part of the Yakima fold belts. But I can't seem to tease out, is this more of a clockwise rotation story? Hello, hang on. Is this more of a clockwise rotation story? I think it is. But is some of this tilting of original flat layers more tied to this Cascade uplift in the guts of the north-south range? I mean, we live in a beautiful area. What can you say? Here is the best cartoon I have to show the walls of the Columbia River Gorge looking north. You're looking from the Oregon side to the Washington side. And here's the Cascade Volcanic Arc and the lofty peaks. Mount St. Helens is nearby. But here's our Grand Ronde lavas that were originally flat on top of Ohanapakash and Eagle Creek Formation, in respectively the 30s and the 20s. And here's our brown. Here's our German chocolate cake that has been uplifted more than 3,000 feet in the heart of the gorge. So we're getting to the message now that, yes, through much of the history of the Cascade Volcanic Arc, the SWAC time during the 50s, before the Cascade Volcanic Arc even got started, the Ohanapakash, the 20s, and the Basalt time itself, Ken Clark helps us see that there wasn't much of a mountain range where we now have the Cascade Volcanic Arc. I mean, Ken has through-going rivers during much of this time. So Mackin was on to this, publishing first that little pamphlet, Cascade Landscapes, in 1947. J. Hoover Mackin, and he had a geologist/illustrator, Alan Carey, helping him out. Can I read some of this very briefly to you? The uplift of the Cascade Range. This is J. Hoover Mackin. It's easy to bend a telephone book into an arch, but it's very difficult to produce a simple arch in corrugated cardboard in which the corrugations run at an angle to the trend of the arching. He's talking about a Cascade uplift against a Yakima fold and thrust belt. The uparching of the Cascades is a mechanical problem of the latter type, in which the corrugations are folded structures in the older sediments locally stiffened by irregular masses of granite. So whereas the range is in a very general way a north-south belt of crustal uplift and volcanism, it is everywhere complicated in detail by fractures and bucklings in many different directions. When the outpourings of the flood basalt eruptions, this is 1947, finally ceased, the lava surface extended as an almost featureless plain covering much of Washington and Oregon and extending entirely across the site of the Cascades to the ocean. I think maybe at the time the thought was many of the basalts of the Olympic Peninsula might be Grand Ronde lavas. We now know that they're far too old and they have the wrong chemistry for that. Those are the crescent basalts, otherwise known as Silesia, that formed offshore. But at the time, I think that was the thought, that we can continue those great lavas all the way to what is now the Olympic Peninsula. And here, Mackin is suspecting that the uplift is younger than 10 million years, which we still suspect. Although I don't know how much progress we've really made on the question, to be totally honest. So we're getting into the detail now. I'm shooting for a couple of key moments before we quit here tonight. Here's my photo. I don't take that many photos, but here's my photo from Lion Rock, north of Ellensburg. And here is the end of the line for the Grand Ronde lava, and it just stops. And there's 1,500 feet of this vertical thickness of this material. Why would it just stop there? I actually honestly don't think anybody in geology agrees that these things are all just going to put on the brakes at exactly the same spot. But it's a question of, did these lavas go another 5 miles, another 10 miles? Did they cross the current crest? Did it cross Snoqualmie Pass area today? But it's this kind of dramatic, breathtaking put on the brakes. Come on, man. Gary Paul in the crowd. Gary Paul giving us a stunning shot from the same exact location. What is going on? What is the significance? And might there be any scraps of these lavas up in the Cascades today? Thank you, Gary. This is a map from Don Swanson. If you know the local geography well, this line right here is that very sharp boundary, the western boundary of the German chocolate cake. And it squiggles, and it squaggles, and it works its way towards Mount Adams. I think some geologists think that Mount Adams itself is built on Columbia River basalt lava. Well, we can't prove it. We don't have that relationship very clearly at the surface. A map from Andrew Sadowski, brown, around the Kittitas Valley where you're sitting right now. It's all German chocolate cake, but it abruptly stops in places as you head into the high Cascades. So you can continue this down in the Columbia River Gorge, but you cannot continue it further north in the Washington Cascades. We know the answer now. The high Cascades have not always been high. That's a recent story. So all through the 40s, it was low. Stop. Auhanapikosh, those green rocks, tell us that there were submarine eruptions of the Cascade lavas between 32 and 26 million years ago. Maps from Tom, photos from Lindsay, showing all these rocks, Auhanapikosh rocks, which are now high in the mountains, up by Mount Rainier National Park, with the Tatoosh magmas coming up through the Auhanapikosh. Those Auhanapikosh layers today are high, but they are submarine eruptions. Stunning, isn't it? That as recently as 26 million years ago, today's Cascades was underwater, below sea level. And the rocks tell us that. I don't know how to tell that, but people who know how to study the details and the textures of some of these volcaniclastic deposits within the Hanapikosh can see that submarine story. Green, Hanapikosh. We get it. We get it. If we flash forward to the red time, the Roaring Twenties, the little personal human interest now, and we're getting to one of the more important emails that I have to share with you tonight. Some of you are aware of Paul Hammond, a longtime geologist, geology professor at Portland State University, and he passed away just a few months ago. And Paul's notes, his samples, his maps have all been preserved and are now being cataloged at the Washington Geological Survey. And I intersected with Dr. Hammond just a few times, about 10 years ago, and I want to report on one little day that I had with Paul and some others on this trip. Here are some of Paul Hammond's maps from the Fifes Peak Formation in the Roaring Twenties in the area between Yakima and Mount Rainier National Park. All sorts of impressive detail mapped with more than 50 field seasons in the Cascades. And I'm mentioning Paul Hammond tonight because he was a big believer of the potential for these flood basalts crossing through the Cascades. So he's mapping stratovolcanoes between Yakima and Chinook Pass. He's visualizing during the basalt time that the basalts are threading their way through between these islands of stratovolcanoes in a low coastal plain. He's not the first to think that. Don Swanson before him, or at the same time as him, was also publishing on something similar. There's up to 1,700 feet of Grand Ronde lava near the Tieton Dam and the Tieton Reservoir, in that area along U.S. Highway 12. Eric Cheney's found some unconformities above and below this brown time. But I'm building towards an email which I found just recently, and I want to share it with you. Here are some Paul Hammond maps showing fingers. It's not orange, but it could be. Orange worms working their way and finding low spots in the low Cascades to potentially cross. And I'm adding some dates now. He's got some old ghost volcanoes. The Tieton volcano, first discovered by Don Swanson. Edgar Rock volcano, documented by Paul Hammond himself and some grad students along Washington 410. And then here comes our Grand Ronde lavas swimming around each of these standing sentinels at that time. It's the Grand Ronde lavas that's doing it. Andrew Sadowski had this cute little prop in his kitchen to help us visualize that those older Grand Ronde lavas were erupting and filling the low places in the ice cube tray. And by the time we get to a bunch of water during the youngest of the Grand Ronde time, we can cover the entire tray of ice cubes. Geophysically, we have connections, ways to follow things in the subsurface through the Cascades. Well-known crustal faults, reverse faults from the clockwise rotation that can be followed geophysically over to the west side. So why wouldn't we have cross-cascade valleys doing the same sort of thing? Yeah, man, I'm asking about the orange worms. Come on. And we got Chehalis area and the Yakima area. And basically I'm proposing, and Paul Hammond was proposing, some sort of continuation of the flood basalts through U.S. Highway 12. If you've been over White Pass, if you followed U.S. 12 over that area, that's essentially the pathway that has been proposed. So here's a day, Sunday in August of 2015, where I spent the entire day with Paul Hammond. And as I was searching for an old email, I found this one. Can I read it to you, please? This is me reporting to Andrew Miner and Tom Foster, August 24th, 2015. Andrew and Tom, I just spent today with Paul Hammond at Fifes Peak Volcano. I learned a lot. Paul was shotgun in my van. He talked from 9 in the morning until 4 in the afternoon, nonstop, but in a nice way. Handful of Portland State geologists and students with us, 2 gals he had working for him that summer. I was surprised by Paul Hammond peddling the idea of everything in the Cascades was once under a blanket of Ellensburg Formation, including the older Cascades. The young Cascades uplift removed much of the blanket of Ellensburg Formation. Paul Hammond says some Ellensburg Formation is on the west side of the Cascades and says that Crystal Mountain is a big wad of Ellensburg Formation. Quote, the Ellensburg Formation is telling us about Cascades uplift. We're just not listening, end quote. So one of the reasons that I'm spending most of this spring's Geology 351 class studying the Ellensburg Formation is this email that I found a few weeks ago. I want to listen to the Ellensburg Formation, and I want to hear what the Ellensburg Formation is telling all of us about the uplift history in the Cascades. Finally, Paul went on, apparently the whole day, I don't remember much of this, lots of love for Hoover Mackin from Paul's early days at the UW when he was a student. He says Mackin got a bad rap for liking Columbia River basalts crossing some of the Cascades. He says there's thick Columbia River basalts at Steamboat Rock near Indian Hills volcanic field. Proves major crossing of the Cascades through that channel. So that was something I had forgotten, and then this past winter, Sky Cooley, who's sitting in the audience, alerted me that there was a mountain truly called Steamboat Mountain up in the Cascades between Adams and St. Helens, north of Indian Heaven, that is in the Cascades between these two stratovolcanoes, and it's Columbia River basalt lava. There's one scrap that we have. This is a place you can hike, Steamboat Mountain Trailhead, Steamboat Mountain Lake Trailhead. And this from John Lasher just the other day. Lasher emailed me and said, I just found this map that Paul was working on with some Grand Ronde lava at Steamboat Mountain, some similar Grand Ronde lava at Squaw Butte, and he drew a cross-section that was not published showing the side view of those two pieces. So it's this kind of connecting the dots between Yakima, Grand Ronde lava, Divide Ridge, Grand Ronde lava. I wouldn't be shocked if the Goat Rocks volcanic complex has a basement of Grand Ronde lava. And there's two young undergraduates sitting right over here, Jess and Julie, who are working under their professor, Hannah Shamloo, and they're working on those basalts right now and trying to get the chemistry of the basalt basement beneath the Goat Rocks volcanic complex. And in the next month, they're going to decide with their results geochemically if that's Grand Ronde lava or not. If it is, results coming from our geology building in Ellensburg, that would be fun to have another breadcrumb to tie these Grand Ronde lavas up into the high parts of the Cascades, because Goat Rocks is right up there at the crest, Pacific Crest Trail country, for goodness sake. Some say the Ellensburg Formation on the west side of the Cascades. That's it. We're just not listening. So this is what the Cascades, this is what the Ellensburg Formation looks like on our side of the Cascades. What kind of stories are yet to be pulled out of these deposits of conglomerates, river sands, and other things to help us know more about the uplift history of the Cascades? All the yellow Ellensburg Formation. We're wrapping up with some final thoughts about uplift and what's driving it. Sky Cooley made this beautiful diagram. If you're watching this on YouTube, you might have to just hit pause so you can read all this stuff. But there's many different kinds of evidence in eastern Washington, and each kind of evidence, whether it's plant fossils in the Ellensburg Formation, calgreets and Hanford boreholes, dryland plant species, geomorphology, tilt on the Thorpe Formation, all these different kinds of evidence east of the mountains is a way to speculate on when the high Cascades started to uplift. So you can go anywhere between 15 million years ago and 3 million years ago to find a scientific paper that talks about the beginning of the Cascade rise. But Sky continued with some cartoons made for our learning community. And Sky is thinking that in the 10 million year range, we have low relief, low summits, low passes in the Cascades, no barriers. And by 7 million years ago, perhaps, that's when we start seriously making the high Cascades with higher summits. The passes might still be low, but there's a partial burial, and the rain shadow effect is weak, but it's getting started because of the calcretes in eastern Washington. And according to Sky Cooley, by 4 million years ago, we definitely have high topographic, orographic divide, west versus east, and all sorts of details backed up with that. I think we're going to pass through some of this. There's speculation about changing ocean plates offshore the Pacific Northwest that might be a trigger for this renewed uplift in the high Cascades. If you're waiting for that answer, nobody seems to know. Even the idea that massive amounts of magma rising in the Cascade volcanic arc might be the fuel, might be the engine for the uplift. Maybe not a tectonic story, but magma flux increasing the elevations in the Cascades. We're truly out to lunch with details, and we're in the stage of weighing many different options, including an uplift starting as recently as 3 million years ago. This is the last set of photos. I want to finish with Hannah Shamlow's Goat Rocks project, which is continuing at Central Washington University. The Goat Rocks was a series of volcanic eruptions between 3.2 and 500,000 million years ago. And the reason I'm including it is that up here high in the Goat Rocks country, there was an eruption of the Titan andesite lava. There were actually 2 separate Titan andesite lava flows that erupted out of Bear Creek Mountain volcano and flowed almost to the Fred Meyer in Yakima, Washington. And the reason I'm sharing it with you is that those columns along US High 12, they look like Grand Ronde lava, but they are not. They're the Titan andesite. Those royal columns are in the older of the 2 Titan andesites. Here's the Goat Rocks, eruptions, and the Titan andesite flowing the wrong way. This is lava coming from the west to the east. It's like the opposite of what we've been doing tonight. So why in the hell am I adding this at the end of this lecture on flood basalts? The reason is, if you look carefully along this route for scraps of the Titan andesite flows, plural, and you can find the Titan andesite because it's beautiful in hand sample. There's 2 flows on Darrell Gussie's maps. There's a pink and a purple. The purple Titan andesite lava erupted 1.64 million years ago, and the pink erupted 1.39 million years ago, younger. There's not much time elapsed, right, between these 2 dates. And yet when we look in this valley and look for scraps of this Titan andesite older and this Titan andesite younger, there's whole sections in the Titan Canyon where everything's gone. A 1.5 million year old lava flow is almost completely gone. And even more impressive than that, the time between the 1.64 million year old lava, which presumably filled the entire valley, and the younger Titan andesite flow that came not much later, look at all the purple that's been scalloped out of there. What the hell is going on here? Why is so much rock being removed at such a short amount of time? If that kind of erosion is possible in one little valley between Yakima and White Pass, why couldn't we remove large portions of a German chocolate cake in the high Cascades? Yes, erosion appears to be a major story in the Cascades, from the olden days and from very recent time during the Ice Age. Backcountry Gary Paul, Cindy Shaw, the Cascade Range in the Pacific Northwest, and most specifically, the state of Washington. Thank you, everybody, for coming tonight and for coming to all of these lectures. I love you.